Welcome to next lecture. In this lecture, we will further continue our discussion, about the communication channel, which we call as discrete memoryless channel. So I again repeat it. So here is this model of discrete memoryless channel. So basically, we have input. See, you transmit something, okay? So that we call as input, and then you have a communication channel, and then you receive some output. So this simple, block, they depict most of the practical communication scenarios. So you may be transmitting some signal or some message from your mobile, and it first goes to base station. So your base station is receiver and your mobile is transmitter, and in between the wireless medium, that is the channel. Or it may be a telephone conversation, then the wireline channel is there, or you may be communicating over optical fiber, whatever it is. So in information theory, we provide the mathematical modeling without going into details that what actually it is. So as you know, we model the x input as random variable, okay, x taking values from some set. As an example, if you are transmitting just binary zeros and ones, then this set is simply set of 0 and 1, okay, and the input random variable is simply then the binary random variable. So channel may change something. It may change 0 to 1, 1 to 0. It may erase 1 or 0, whatever it does. Whatever you receive, we represent that as another random variable y, okay, and we assume that it takes values from some set capital script y. Again, for binary case, one of the possibilities is that this y also is a set of binary values, only 0 and 1. But there can be much more general alphabets also, as a combinations of 2 zeros, 2 binary bits, and so on and so forth. We'll see some more examples later. Now here is one question which we already have answered. The question is that what is the, so suppose if you have the source, you don't know what bit will come out of the source, right? So you are basically uncertain about the source, right? If you observe the source, so here is the source of bits, okay, so a random bits are coming, at least from observer point of view. You don't know what will come out. So what is your uncertainty about x, okay, or how much information will you gain after you observe the x? So you know the answer. So if you know the probability mass function defined over x, then the answer is entropy of x, defined as px log to the base 2 px of x, okay. now here is another question. You transmit this x now over the channel, and what you receive is y. Now the question will be, after observing y, okay, now after you observe the y, what will be now your measure of uncertainty about x? Measure of uncertainty, or how much information will you gain about x? So that is called conditional entropy, okay. So first of all, to define it, let's assume that suppose you observe a particular value y is equal to some yk, okay. So at the receiver, maybe you have transmitted 0 or 1, but at receiver you are pretty much sure you received 1 or 0. Let me call it yk, small yk. So particular value. Now we are fixing the value of random variable here. What will be the entropy? So we will write it like this: entropy of x conditional over that I receive y is equal to small yk. Now how will we define it? So if you see, if there were no yk observed, then your answer would have been summation. Okay, I will run j is equal to 0 to j minus 1. What is this capital J? So if you remember previous lecture also, we assumed that the set y can take values y0, y1 up to y capital J minus 1. Suppose in binary case this j is 2, simple. And if there were no y observed, then your answer would have been p of x j, right? I will just keep space here, log to the base 2 1 over p of xj, correct? But you have observed now yk, so it will be conditioned over yk. Conditional probability will enter here. Very simple. I mean, it's quite obvious. There is nothing big here. Now, if we have taken here a particular value yk, right? But actually y can take any value, right? It can take y0 with probability py0, right? Or it can take y1 with probability p of y1, so on so forth, j minus with probability p of yj minus 1. So on an average, what value can it take? So it can take, so you have to recall expected value of any random variable y is the value it takes times the probability, correct? So we can in some sense say the expected value of this quantity, conditional probability for particular value of y, this expectation is with respect to y. That means it will be equal to summation the value it takes, that is h of x given y is equal to yk, that is the value for particular yk, time is the probability. Okay. Now yeah, so k is equal to k minus 1. I think I have written here something, right? Okay, sorry. So basically according to book notation, y takes k different values and x takes j value, sorry for that, x0, x1 to x j minus 1. Okay. So in various cases this j and k are same, that is number of values what x can take is same as number of value what y can take. In some cases it can be different also. So now what will be this equal to? K equal to 0 to k minus 1. Now in in place of h of x equal y equal yk, I will write back the expression written above. Let me call that equation 1. So from equation 1, we get, so there is outer summation k. Now h of x given yk is summation j is equal to 0 to j minus 1, p of xj given yk, p of yk is here, log to the base 2 1 over p of xj given yk. Simply I have put that equation here. Now what do you see here? You see conditional probability of x given yk times probability of yk, that is equal to joint probability. So it is p of xj comma yk log to the base 2 1 over p of xj in yk. Right? So we have used the fact that conditional probability is equal to joint probability divided by this fact we have used. Now this is denoted as h of x given capital Y, and this quantity is called conditional entropy. So it is the average amount of uncertainty remaining about the channel input after the channel output has been observed. Okay, that is when you observe Y, then what is the uncertainty, what is the information average amount of information or average uncertainty that remains about the X. Now with this we can basically motivate ourselves to introduce one other important quantity. So that quantity is, let me give the motivation for that. Let's see h of x. I recall h of x, it represents, it quantifies the uncertainty about the input, uncertainty about x without observing y. Okay, suppose if you are at receiver, the only information you have about the channel is the probability with which, let's take example, suppose your x can take only 0 and 1 values with some probability, suppose probability of 0 being p and probability of 1 being 1 minus p. So this thing, that probability of 0 is p, probability of 1 is 1 minus p, but you don't know what was transmitted. So you have what uncertainty you have about it, or what is the average information. So it is h of x, right? So that is minus p log p minus 1 minus p log of 1 minus p, that we have done binary entropy. Now after you observe y, what is the uncertainty, or what is the sort of information? So that is h of x given y, okay, which we have defined like this. Definitely to compute h of x given y, you need the knowledge of conditional probabilities. Suppose someone tells you these conditional probabilities. Now h of x is the uncertainty without observing y. I subtract from this the uncertainty which remains after observing y. Definitely when you observe something, when you get some additional information, your uncertainty will decrease. See, suppose you don't observe clouds, you are just sitting in your room and someone asks you, okay, what do you think, how much probability is there that it will rain? He is not telling you anything, whether it is sunny or whether there are clouds or not. Definitely you will have more uncertainty, you will be more uncertain about having rain or not. But now if someone tells you side information that, okay, yeah, I saw just there are clouds in the sky, now your uncertainty about whether it will rain or not will decrease certainly. Similarly, you observe y is not the exactly what was transmitted, but it has some relationship with that. Channel has changed somehow input, but still y contains information about x. If someone tells you that y, you will be less uncertain about x. Now the difference between the two, what you know about x without observing the channel, and what you know about X after observing the channel, this quantity is very important, and it has separate notation. It's called I of xy, and this is called mutual information. Okay, and it is actually a measure of uncertainty about the channel input which is resolved by observing the channel output. We will get more about it. It's in some sense sort of a flow of information, how much information y conveys about x. And see, right now you are hearing to these definitions in the context of communication system, but as I told, this x can be any random variable. It can represent anything which is random. Y can be any other random variable, and I of xy is still a mutual information. It is not necessarily it need not be necessarily a communication system. Okay, so suppose very recently people have done a lot of work on neural networks, and they represent x as the input to the layer. So there are several layers in neural networks, right? And they represent as y as, suppose y1 as output of one layer and y2 as output of one layer. Suppose there are n layers, and yn of output of nth layer of your neural network. And then suppose you model your system such that the input is modeled as a random variable and output of layers is also modeled as random variable. Then you can define mutual information between what you get at the output of one layer with respect to the input of that layer. And lot of computational inferences and lot of insights have been developed about, especially if this number of layers n it increases. So then that paradigm, as you know, is called deep learning. Okay, so there has been a lot of work on using mutual information and entropy to quantify a lot of algorithmic quantities in deep learning paradigm. Okay, so this is just an example, as we have a lot of people from computer science background, so they should not think that we have learned something irrelevant. Okay, so these days if you pursue some very good course on machine learning, part of curriculum is information theory there. Okay, a lot of cost functions are defined in terms of mutual information and entropy. So more will come. And also, if you are suppose if you are a computer security guy, and if you are interested in cryptography, so entropy and mutual information is used to quantify randomness in cryptographic codes also. Okay, so this is just a motivation that it's quite general. I am talking right now maybe mostly in terms of communication system, a transmitter receiver. That is because we are going to study digital communication. Otherwise, mutual information is a general thing. Okay, so if you have just any system where you have x as one random variable and some observation y as another random variable, x and y are related to each other, and x has a probability mass function px of x, y has py of y, and how are they related with each other? They have a conditional probability py given x. Okay, you can always define a mutual information. How much information y contains about x? That will be h of x, the uncertainty in x without observing y, minus h of x given y, the uncertainty in x after observing y. Okay, and we will see that it is symmetric. It is also same as if you have what uncertainty you have about y without knowing anything about x, minus if some genie tells you x. Okay, someone tells you that what was transmitted, then what is uncertainty in y. So both are same. Okay, now let's look at another way See, I am interested in this thing. There is a x at input, y at output. I want to know that how much, y is related to x. See how much, this is in quotes, y is related to x. See, if x and y have no relationship, we can clearly say that the mutual information between x and y should be 0, right? So you want to know about weather, and someone is telling you that there is a traffic jam in Lal Chowk. So traffic jam in Lal Chowk will have no impact on knowing whether it will rain or not. Okay, so in that case, mutual information between the two things, one is the traffic status of Lal Chowk, let that be x, and y, let it be the prediction about weather, it is 0, right? But certainly if x is the information about clouds and y is the information about whether it will rain or not, certainly x and y are related to each other. Their mutual information will not be 0, right? Now how do I quantify? See, if you know from probability point of view that if x and y are two random variables, right? They are two random variables, and if they are independent, then what will happen? Their joint probability mass function p of xy can be written as the product of individual marginal distributions, right? So this is one extreme when they are independent, and if x and y are not independent, then you know that we cannot write it in this way. Rather, there is a simple formula. You can write py of py given x, p of x. You can also write px given y, p of y, right? General formula. So you can't remove the dependency of x and y here. You can write it on this way. Now these are two extremes, right? So there is one. So here is one thing I will write. So in reality, the truth is that x and y depend on each other. Okay. So here is a guess that they are independent. Okay, this is the notion for independent. How far are these two beliefs? One is that x and y are related to each other, so they have a joint distribution only. The other is that they are. So can I say that it is the relative entropy or divergence between the two scenarios? In one scenario, you are assuming that x and y are not independent, they have the joint distribution, versus x and y are independent, so their joint distribution can be written as this. Just look at it. Okay, so this is the divergence or relative entropy between the belief. One is that joint distribution, that is, you believe that x and y depend on each other. The other is that they are independent. Now how will it look like? So I'll start writing it like this. So log of pxy of x given y divided by px of x py of y. Okay, and then if you remember that d of pq, so it was summation p log of p by q, right? So summation will be now here, since we have x and y, so I will have double summation, one with respect to x, one with respect to y, and here will be the p of xy. Okay, now this is also mutual information. That is the thing, we will prove it in next lecture. So this is also mutual information, and you see the beauty it has, this equation has. Now suppose if it is true that x and y are independent, then if it is true, then you know that p of xy will also be written as p of xx p of yy. So what will this become? log of 1, right? This will cancel out, which is 0. So it means if x and y are really independent, then this is the mutual information, it becomes 0. Okay, so in next lecture I will show it to you. In fact, you can take it as a homework also. You should try it first yourself, that mutual information, here's the notation, you should remember this: I of x semicolon y. Okay, mutual information is defined as, we first motivated ourselves with this: uncertainty after observing x without observing y minus uncertainty in x after observing y, same as uncertainty in y minus uncertainty in y after observing x, and same as relative entropy between the belief that x and y are not independent, they have joint distribution, versus x and y are independent, so their joint distribution can be written as product of individuals, so which is also written as summation something. Okay, so now we have now defined second another important quantity of information theory called mutual information. And in next lecture we will again sort of show that this relationship is true, and then we will study some of the channels and compute mutual information, and we also will introduce the notion of something called channel capacity, and I will then state the famous theorem of Claude-Shannon's paper, which is called the most remarkable theorem of 20th century, which has revolutionized the whole world of digital and wireless communication, and also it has revolutionized the world of storage. Okay, I will have some comments over that. If you are able to store huge data on your pen drive, and you are able to compress things, there's a role of information theory there. And also his theory is still continuing to do, as I just gave an example on deep learning. So similarly in other fields, in the area of cryptography, statistical learning, reinforcement learning, so in a lot of areas this theory is continuously giving us a lot of insights. But in particular we will be mostly concentrating on communication system. Nevertheless, I will be giving examples and motivations from other computer science and other fields also. Okay, thanks.